Assalamualaikum and greetings everyone. We are from the Expert Team A, which have Design Team 1 and Design Team 9. And we are going to give you guys a pre-teaching project about sizing, costing and mechanical design of heat exchanger by our expert team. So as an introduction, so what is heat exchanger in basically? So basically we are going to use heat exchanger to heat, cool, condense or vaporize the process stream. So for sizing, we are using this to determine the physical heat exchange surface area that are required for the heat exchanger to perform the job. So for the costing, basically we want to use something, if we want to have something, we need to determine the purchase cost of the unit that so that the project budget can be planned properly. So purchase budget CP is basically proportional to the exchange surface area A. So for shell and tube heat exchanger, this is basically the standard heat exchanger that we use. They are designed according to TIMA and S codes. It have a high versatility and also a good design which have fixed head, floating head, YouTube and get. So for double pipe heat exchanger, we have a small scale specialist, which is for the surface area less than 200 feet square. It has a simple design for the outer pipe and the inner pipe, and the ideal for non-demanding application where the shell and tube is too big for the process. And the next one we have air-cooled fin fan unit. We have this to use when the process must be cooled by air. This is common where cooling water is expensive or we don't have cooling water in the area. And lastly, we have compact heat exchanger, which have flat end frame, spiral plate, and pad fin for the design. It has a high surface area in the small footprint. Like the double pipe, we really use the non-demanding application for process. So in summary, we have shell and tube for the default or all sizes. We have double pipe heat exchanger for small scale surface area, and we have air cooled fin fan for the air cooling, and we have compact heat exchanger for the space saving or non-demanding tasks. So let's proceed.
Okay, now for the temperature driving force in shell and tube heat exchanger. In a real life shell and tube heat exchanger, the flow is not purely countercurrent or co-current because of the multiple tube pass and the single shell pass. The flow direction is a combination of both co-current and countercurrent. Because of this mixing, the log mean temperature difference that we calculated is actually lower than true driving force, so we introduce a correction factor called Ft to get the real mean temperature difference. The simplest expression for delta Tm is valid only when these 5 assumptions are true. The first one is steady state flow, second countercurrent or concurrent flow, third overall heat transfer coefficient U is constant, fourth only sensible heat change, no phase change with constant specific heat, and lastly no heat loss to surrounding. Okay, now for the equation 12.2. This equation is for the basic heat transfer question. And then for the equation 12.3, for pure countercurrent or co-current flow, we will use this log mean temperature difference equation. And then for equation 12.4, will be for multipass shell and tube heat exchanger. And then we also can use equation 12.5 and 12.6, and then we will get the complete equations, which are 12.7. This Ft is usually read from charts, but the formula is shown here for reference. Moving on to the overall heat transfer coefficient U. U is estimated from the sum of all individual thermal resistance. In practice, we don't always calculate every resistance from scratch. Instead, we will use typical value of U given in the table 12.5 in the textbook. The U value in that table already include the following factor: RFO for the outer side and RFI for the inner side. So the U value are ready for real design. We can refer U to the outer area, inner area or mean area in equation 12.8. The formula for the area can be seen in the equation below it. And the full expression for UO and UI are given in the equation 12.9 and 12.10. Here is the typical step-by-step design procedure for shell and tube heat exchanger. The first one, we will define the duty. Here we will know Q, flow rates, inlet and outlet temperature. And then second, we will collect the properties such as density, Cp, viscosity, thermal conductivity at average temperature. And third, we will select the type such as shell and tube or number of the passes of the heat exchanger. And fourth, we will select the trial value. Here, we will pick a trial overall coefficient U from table 12.5. This will be our first guess. And fifth, we will calculate mean temperature difference, delta Tm. We will use the delta TLM and the FT correction we just learned before. And then 6, we will calculate the area required using equation 12.2. And then 7, we will decide the heat exchanger layout, such as choose tube diameter, number of tube, shell diameter, alpha spacing, or tube passes. And 8, we will calculate individual coefficient. Now we will compute the real shell side and tube side. And 9, we will calculate overall coefficient. We will get the actual U and compare it with the trial U from step 4. If they are very different, we will go back to step 6 and recalculate the area. And lastly, we will check pressure drop. Here we will calculate delta P on both shell and tube sides. If the pressure drop is too high or too low, we will return to step 3, 4 or 7 and revise the layout.
Example 1. Design a shell and tube heat exchanger to cool to 60,000 lb per hour of 32 degree API kerosene from 400 to 225 degree by heating 35 degree API distillate from 100 to 200 degree F under the following specification. Neglect the tube wall resistance. Use inch 16 BWG tubing, OD 0.75 inch and ID 0.62 inch. Use 1 inch square pitch. Place kerosene on the shell side. These are the following information given for the shell side fluid 42 degree API kerosene and tube side fluid 35 degree API distillate, and according to heuristic 54, for shell and tube heat exchanger, tubes are typically 0.75 in OD, 20 feet long and on 1 in triangular spacing. Step 1. Calculate the heat duty. Q equal to mCp delta T equals to 6457500 BTU per hour. Step 2. Calculate the required flow rate of API distillate. Mi equals to Q over CPI delta T equals to 129150 lb per hour. Step 3. Estimate overall heat transfer coefficient. From table 12.5, the value of U is estimated U equals to 40 BTU hour feet square degree F. Step 4. Calculate log mean temperature Rs and feet. So the R is 1.75, S is 0.33. Continuous for the FT calculation, which is FT equals to 0.87. Next step, calculate heat transfer area A1. First, we calculate Q and then A1 equals to Q over UFT delta T LM equals to 1168.74 feet square. Since the heat transfer area is larger than 200 feet square, therefore a floating head shell tube heat exchanger is chosen. Step 6. Calculate total cross-section area per pass ACI and total cross-section area per tube ACT. ACI equals to 0.1407 feet squared, meanwhile ACT 0.0021 feet squared. Step 7. Calculate number of tubes per pass N, which is NT equals to ACI over ACT, approximately 68 tubes per pass. Step 8. Calculate heat transfer area per tube at and number of tube passes NP. AT equals to pi DIL equals to 3.25 feet squared per tube. NP equals to AI over AT and T, approximately 6 passes. Lastly, step 9. Select shells diameters D. From table 12.6, assume shells diameter D equals to 31 inch. Will hold 6 times 68 equals to 408 tubes on square pitch in a 6-pass exchanger.
this is the Excel tool for heat exchanger sizing. First of all, you may key in the information of fluids and also shower and tube based on the given question. Next, you have to estimate the overall heat transfer coefficient referring to table 12.5, basically for shower and tube heat exchanger. Then all of the parameters needed are calculated automatically here. Then we can get a final outcome which we want, which is the number of tube passes.
Moving on is the example for the process cost of heat exchanger. So we are using the question from the previous example of sizing. And here is the extraction of the data from the previous example, like the tube length, area, and we do make some assumption for the design pressure on the south side, which is 150 psig, and the material for the tube and shaft, we are using the carbon steel, as is the most common material used in the heat exchanger. However, the selection of material should be based on the liquid that fall in your tube and shaft, not 100% using the carbon steel. Another assumption we make is the CE plant cost index was 567 in year 2030 and increased to 845.5 in year 2026. In order to calculate the process cost of a heat exchanger, we need to use the equation 16.43. And you can see that there's a lot of unknown inside the equation. Therefore, we need to solve one by one unknown. First is the base cost, CB. So we are using the equation from 60.39, which is the equation for folding head. If we are using the different type of cell and tube heat exchanger, we need to use different equation. And from here, we can calculate the CB value. Then we can calculate the material of the consumption factor, Fn. We are using the equation 60.44. And to solve this equation, we need to use the table 60.25. And then we can see that there are several different types of the material of the shell and tube. If we are using a different type, we need to choose the accordingly material and choose the A and B value and then plug into the equation. And from the table 60.25, we can see that for carbon steel and carbon steel, the A and B are equal to 0. So by substituting into the equation, we can get the Fm equal to 1. Then is the FL, which is the tube length correction factor. We can find this table in page 462, as our tube length is 20 feet, so the FL is equal to 1. Afterward is the pressure factor, which we need to use the pressure, and the pressure must be in units psig. And we are using the equation for 60.45. By substituting the pressure, we can get the FP equals to 1.011. After getting the 4 unknown, we can substitute it into the equation 60.43, which is the FOB process cost CP. And then we can get the CP value. After that, we can get the CP value at 2026 years. By substituting the base cost, which we calculate from the previous one, and then time with the index over the base index. And then we can get the process cost at 2026, which is the current year.
Next, we move on to the Excel calculation for the estimating purchase cost of the heat exchanger. First, we start with the extraction of the data from the calculation of the heat exchanger sizing. From the given data, we identify the key parameters such as surface area, tube length, design pressure, and we also include some assumption for the example adjusting cost index value to the current year. Okay, so for the step 1, we calculate the base cost of the heat exchanger. In this example questions, we use the floating head. And also there is also different type of the heat exchanger such as fixed head, U-tube, and also kettle reboiler. Depends on what type of heat exchanger that we need to calculate. Next, for the step 2 where we determine the material construction factor, this factor depends on the material selected. We refer to the standard table and input the corresponding value into the Excel from the table 16.25. In the step 3, where we calculate the length correction factor, we use the given tube length and also apply the appropriate formula in the Excel. From the table, we can find in the book page 462. Next, in this Excel, we show the answer for the pressure factor, also the FOB purchase cost based on what type of the heat exchanger we use. Then for the last step, step 6, we adjust the cost using the cost index to reflect the current economic condition. This gives us the updated purchase cost of the heat exchanger.
Okay, next, moving on to the mechanical design part of a typical heat exchanger. So in this slide, we are showing a typical design for a shell and tube heat exchanger, which consists of the components such as the tube, the shell, the baffle, as well as the inlet and outlet ports of the process string involved. While the right-hand side diagram shows the typical design diagram where we can done using the AutoCAD software. So from the upper part, it shows as the side view cross-section of a shell and tube heat exchanger. So basically, we need to show the dimensions of the critical dimension of the heat exchanger, including the tube length, the total length of the heat exchanger, the shell diameters, as well as the design dimension of both front and end head of the heat exchangers. While the bottom part is showing another view of the heat exchanger, where we need to show the dimension and the design view of how many tubes are involved within the shell body, as well as the tube diameter and how we arrange the tubes within the shell. Okay, in this slide, it's showing the more detailed mechanical design of a shell and tube heat exchangers, specifically for the overall shell bodies. And it consists of the front end design, shell design, as well as the end head designs. So basically, the selection of the specific design depends on how many shell and tube passes, easy for cleaning as well as for maintenance process.
Lastly, for specification sheet, TEMA, TEMA specification sheet will be used. It's a standardized document used to define the thermal and mechanical design requirements of shell and tube heat exchanger. It is divided into 8 parts, which are: first, customer information; second, performance of one unit; construction information; exchanger configuration per shell, exchanger sketch, design and code requirement, design operating and outside condition, and lastly, material. For the first part, customer information, it is where the general information such as customer or client name, plant location, the unit service, and other are recorded. Next, for performance of one unit, this part specifies the performance of the heat exchanger and the condition of the fluid that will pass through the heat exchanger. This information includes type of fluid passing through, temperature profile of the fluid, operating pressure, and etc.
For construction information, this part specifies the information that are necessary for designing and for construction of the heat exchanger component. This information includes number of passes, safety requirement like radiography levels, corrosion allowance, and PWHT. For exchanger configuration, it specifies the internal geometry and physical arrangement of the component inside the heat exchanger like tube dimension, baffle, and weight. For design and code requirement, this part ensures the exchanger meets legal and industry safety standards. For design, operating and upstate condition, because plants rarely run at a perfect steady state, this section tracks how the exchanger handles this variation in the process. And lastly, for material, this part specifies the material specification for every major component in the exchanger.